Hello everybody. So it's our pleasure to welcome today Professor Shigeru Ida for this presentation about the formation of the early Earth and surface environment. So for you to know, so Shigeru Ida is a very famous researcher in the field of planetary formation. He's a professor at Tokyo Tech, and is also vice director of the ELSI, the Earth and Life Science Institute in Tokyo Tech. So the Earth and Life Science Institute is an institute that has some similarities with IPGP because it tries to mix people doing earth science, geophysics, planetary formation, and also there is a big department more devoted to biology and genomics.
Yeah, biochemistry.
Yeah, and to let you know is that a lot of our students, in fact, go to LC. When you go to LC, there are a lot of former IPGP students, either in postdocs or in PhD. And next semester, you will, or next summer, you will welcome even some undergraduate students of our students that are here. So Shigeru Ida has done a lot of Séminaire and very important work in the field of planetary formation, especially related to phases that you may know called runaway growth of oligarchic growth also. And he's working now today more like on exoplanet and population synthesis. And he has done a series of works that are today very important for the formation of the moons. You know, first model of moon formation for a circumterrestrial disk. So we have invited him for 1 month, but it's almost the end of your stay. So it is the end of a 1 month stay as an invited professor at IPGP. And so it's our pleasure today to hear him talk about planetary formation. Thank you.
Okay, good morning. So, today I talk about the pebble accretion. Pebble accretion model is a new planet formation model. It was proposed very recently, like Omer and Kra 2010, or Lambrecht and Johansen 2012. After that, many theorists actively discuss about the possibility and the implication of pebble accretion. Classical idea was the planetesimal accretion, so building blocks of the planets, kilometer or 10 kilometer sized bodies. But the new idea is a building block of the planet. It's a pebble, like a centimeter, 10 centimeter, or something like that. So first, I discussed about the formation of planetary embryo by pebbles. And I summarized the good point and the bad point of the pebble accretion model. So far, it's not clear planets were formed from the planetesimal or pebbles. It's not clear, but it's a very big argument. But if the pebble accretion model is correct, and then of course the planet formation scenario change. For example, previously planets are formed uniformly in the disk, protoplanetary disk. But if the pebble accretion is correct, maybe planetary embryo formed in a special location, such as the snow line or like some discontinuity of the disk. And in the later part of my talk, I want to discuss about the implication for formation and the surface environment of early Earth, like magma ocean, primordial atmosphere, and water delivery to the Earth, and isotope ratio or something like that. Actually, I got a PhD in the field of geophysics, but undergrad I got a degree in physics, but currently working on the astrophysics. So I go back and forth. So this is just a summary of the planet formation model. In the classical model, first we assume that the planetesimals, like kilometer size or 10 kilometer size bodies, in the disk from the micron or submicron dust grain stick together to make the many asteroid-like bodies. Then they collide with each other. Then planets are grow, and some planets accrete a gas to become the gas giants, and then migrate or something. Eventually, the giant impact occurs, and some Grand Tack model, and for Earth, late Venia or late heavy bombardment. And this is a classical model. But we found that this model, I combined many processes like planetesimal accretion, migration, collision, something like that. Then synthesized the planet formation model and to predict the distribution of the planets, I mean exoplanets. But our team, also other team like a Swiss group, did a lot of effort. But still, planet formation model based on the planetesimal accretion cannot explain the exoplanet distribution. So already many exoplanets have been discovered, and they show some distribution. But it's not easy to explain the model by the planetesimal accretion. On the other hand, theoretically, formation of planets, formation of planetesimals from the small grains, it's really hard. And also experiments, also like collision distribution, collision impact simulation, they all show that it's really hard to make the planetesimal. So the new idea is that not the planetesimal, maybe pebbles. So centimeter or 10 centimeter bodies, it's easy to create. But the problem is that they migrate very fast onto the star. But based on the idea, new model have been proposed. So let me first explain what is the difficulty to form planetesimal uniformly in the disk. It was the original motivation of pebble accretion model scenario. The most serious problem is a radial drift barrier. So here there's a host star, and this is disk. This is particle. In the case of particle, gravity from the host star is balanced with the centrifugal force. It is a Keplerian rotation. On the other hand, in the case of gas molecule, also the gravity from the host star and the centrifugal force, but they have a pressure gradient. As a result, gas rotate always slower than the particle. So for the small particle, of course, aerodynamical gas drag works. Then the particle always suffer headwind, so they lose angular momentum. Then they do spiral into the host star. In the case of micrometer grains, they are strongly coupled to gas, so they rotate with gas, so they don't migrate. On the other hand, if we consider kilometer-sized bodies, like planetesimal-sized bodies, they are almost independent of gas motion, so they don't migrate. But in between, like meter-sized bodies, still their motion is coupled to the gas through the gas drag, but not completely. So that they suffer strong headwind always. And we can easily show that the radial migration speed is like 0.01 AU per year. So the particle, meter-sized particle at 1 AU, they spiral in onto the star just in 100 years. It is really fast. So if we make the kilometer-sized planetesimal through the just a pairwise collision between the grains, then when they become centimeter, meter size, they just go away. So we cannot make a planetesimal. So one way to overcome this difficulty is gravitational instability. I mean that if the small grains get together, but they're not merged, but if their density exceed Roche density, they quickly collapse to make the big bodies. In the classical model, for example, but Roche density is really high, so we need to accumulate solid bodies. In the classical model, they consider that the small grains vertically settle down to the midplane. Then the density becomes higher and higher. Eventually, gravitational instability occurs. But we found that it is impossible because the disk is, in general, turbulent. Even if there's no global turbulence, once dust grains settle down onto the midplane, then there is some velocity difference and the Kelvin-Helmholtz instability is excited. So that we already know that it is impossible. Other idea is radially accumulate because the pebbles migrate very fast, but if there is some ununiformity, they radially accumulate. For example, stream instability or migration trap, the pressure maximum or snow line or something like that. The idea of the streaming instability is a kind of a traffic jam. So here is some simulation by Anders Johansson. This is radial direction, and this bright color show that there's accumulation of solid bodies. So they gradually migrate inward, but once some solid bodies accumulate a little bit, then due to their inertia, so from the back reaction to the gas from the particle, migration speed is slower here. Then the other particle catch up with this dense region. So it repeats, and so eventually their density becomes Roche density. So this is one idea. So the pebble migrates very rapidly, but if some traffic jam happens, then the big clamp can be formed. So this is a streaming instability. But the problem is that many people worked on that, but found that collision for streaming instability to occur require relatively high solid-to-gas ratio. If originally they are dense, solid-to-gas ratio is high, then this instability happens. But usually it's not the case because a pebble migrates very fast, which means that if we see the local density in an oil frame, their density is really low because they migrate very fast. And m dot, so the mass accretion rate is given, but they migrate very fast, so the density is very low. So it's not so clear if the stream instability really occurs or not. At least streaming instability does not occur uniformly in the disk. If such instability occurs, it should be some special location, like a snow line or something like that. So another idea is a migration trap. If there is some pressure bump due to some instability or something, and spiral wave or something, if there is some pressure bump, then the inner part of the pressure bump, pressure gradient is opposite. So the gas rotates faster than the particle. So the particles suffer tailwind rather than headwind. So their migration stopped there. So there are many possibilities, like inner boundary of the dead zone or something. But the problem is that it's not so clear how persistent is the trap. If the solid particle accumulated there, then due to the back reaction, that kind of pressure bump may be smoothed out. So there are many possibilities. So the snow line is a big option. And for formation of icy planetesimals, so classically already discussed about some recycling of hydrogen vapor. So back to the Stevenson-Rooney, 1988 or something. So here's a snow line. So inside, temperature is higher. So the ice component vaporize. But the vapor is a gas, so they diffuse inside or outside. If the water vapor diffuse outside, they recondense. So accordingly, icy material pile up outside of the snow line. This is the original idea. But recently, like Schoenberg and Ormel, they did a very detailed calculation, taking into account the pebble migration, the sublimation, recondensation, and the diffusion. And they find that as long as we consider steady accretion disk, so proton-type disk gradually accrete onto the star. In that case, this enhancement is not so strong, and the direct gravitational instability of ice component may be impossible, and the stream instability it's marginal. So now Sebastian and Ryuki Hyodo and myself are working on this recycling process using the different ingredient and more detailed calculation. Also, the snow line is a possible location to make rocky bodies, not icy. The idea is like this. So, silicate particle is not sticky. So, they can make like a micrometer or millimeter sized bodies, but it's really hard to make the centimeter rocky bodies because they are not sticky. So many people think that the structure of the pebble, icy pebble, is like this. So there are some small silicate particle, and they are covered by icy mantle. So this kind of icy pebbles, if they migrate and they pass through the snow line, then the icy mantle evaporate, and only the small silicate grains are ejected. Because that kind of small grains are strongly coupled to the gas, so that they don't migrate. So the icy pebble migrate one after another, but just beyond the snow line, silicate particles are piled up. Then the gravitational instability may occur. This is another possibility. We already published a paper about that. If we consider accretion disk, if the pebble flux is strong enough, that kind of instability occurs. But this is a very complicated process because here is a sublimation, then the water vapor appears, they change mean molecular weight, and they diffuse out and recondense. It's a really complicated process. We also discussed about working on that. So if this process occurs, then it is interesting because the rocky planetesimals, rocky bodies are formed just inside snow line. And we find that that kind of process occurs like 1 million years later from the CIA formation. So in that case, disk accretion, observationally, disk accretion rate is less than 10 to the minus 8 solar mass per year. 10 to the minus 8 solar mass per year is a mass accretion rate to the classical T-type stars. So the typical age is like 1,000,000 years. So we find that here's our calculation. This is a disk accretion rate onto the star. So that larger value means that initially, so the smaller value means a later evolution. So in the phase of the 10 to the minus 8 solar mass per year, already disk is cool enough. So viscous diffusion, viscous heating is weak enough, and the snow line may be around 1 AU. So the rocky bodies are formed near 1 AU, only 1 AU, very locally. Already, Brad Hansen, 2009, he showed that through the n-body simulation that if the original rocky bodies are accumulated near 1 AU, then he can beautifully reproduce our solar system, like Venus and the Earth, related big bodies, and Mercury and Mars, they are small bodies, and they have orbital eccentricity. But if we start from the uniformly distributed bodies, actually, it's really hard to reproduce our solar system, like Mercury, Venus, Earth, and Mars. Because if rocky bodies are distributed uniformly, of course, there are some bodies inside of Mercury orbit. Also, Mars should be very big, but actually, Mars is small, and outside of Mars, almost no big bodies. Right? Okay. So it is not clear, but still people are discussing. So if the pebble accretion is correct, then the planet formation scenario change a lot. For example, pebble accretion, it is not the inside-out manner. In the classical model of the planetesimal accretion, formation of planets, it's inside-out. So in the inner region, planetesimal surface density is higher, and the Keplerian timescale is short. So quickly, planets are formed. And in the classical idea, planets accrete planetesimal in their feeding zone. So it's a kind of local process until planets start orbital migration. So that initially planets form in the inner region, then it propagates to outer region. So this kind of inside-out manner. But the pebble accretion is totally different. So the pebbles are formed in the outer region, and they migrate, and the small fraction of migrating pebble are captured by the planet. So the orbital radius dependence is really weak. We don't know the later planets or outer planets or inner planets, which is faster. We don't know. It depends on the detailed disk structure, which means that it is easy to create the diversity of planetary system, but it depends on the detailed disk evolution model. So far we don't know. Another property of the pebble accretion is it is very rapid. Pebble mass flux is determined by the growth of pebbles in outer region. So that we can calculate the sticking of small bodies, like micron-sized grains. Initially, they are coupled to the gas, so they stay there. But once they become like a centimeter, 10 centimeter sized bodies, then the migration is dominated. Then they migrate. So we can calculate the, how fast pebbles are formed. Then we can estimate the pebble mass flux. Typically, it is like 10 to the minus 4 Earth mass per year. So it is very high value. So, and the capture probability, it depends on the planetary mass. For Earth mass case, like 10% or 30% pebble flux are captured. But in the case of Mars, it's just 1% or 3%. So that we can easily calculate the growth rate and the growth time scale. So the growth time scale is independent of planetary mass. As long as the planet mass is like Mars or Earth. So it is a 10,000 years or 100,000 years. It's really fast. Even for the 10 Earth mass bodies, it's a core of the giant Jupiter and Saturn. They formed in 100,000 years. It's really fast. But it is possible only for we set up the seed of the planets larger than 100 or 1,000 kilometer size. The reason is as follows. Why the pebble accretion is so fast is that it's a combination of the gravitational focusing and the gas drag. In the case of big bodies, if it approaches the planet, their orbit are just modulated. But in the case of pebbles, they suffer strong gas drag. So once the orbit is modulated by gravitational focusing, then the relative velocity becomes the pebbles becomes large. Then they lose angular momentum energy. So they quickly spiral onto the planet. So which means that for the efficient pebble accretion, we need a big body such that the gravitational focusing is very important. So it is typically like 100 kilometer size or 1,000 kilometer size body. Then the question is how to, where and when make such big body. So it is one bad point for pebble accretion. First, we need to make a big bodies. And another problem is the isolation mass. In the classical models, we call the isolation mass. It's a total mass of the planet in its feeding zone. So if the planet accretes all the planetesimal in its feeding zone, how much is it? In the inner region, it's a small, like a mass-sized body. So maybe after the formation of such protoplanet, we need a giant impact between the protoplanet. But around 5 AU, because the ice condense, also the feeding zone is big enough, then we can make a few or several Earth mass bodies. Then it can be a cores of a giant planet. But in the case of pebble accretion, it's really hard. So once the planet becomes big enough, like Earth-sized bodies, then the density distribution of gas is affected. So then the pressure bump is formed and the pebble flux is stopped there. So it depends on the viscosity of the disk. But using the most recent papers, such pebble isolation mass is Earth mass or rather less than Earth mass for relatively small alpha, so relatively quiet disk. Then the question is how to make a gas giant core. So it's another big problem. So I discussed about the current status of the pebble accretion model. But next, I talk about so what's the implication for the formation of Earth if the pebble accretion model is correct? For example, magma ocean or atmosphere, or isotope ratio, or water delivery. Okay, so this is a classical idea for the formation of the magma ocean by the planetesimal impact. So impact velocity of the planetesimal is almost surface escape velocity from the planet. In the case of the Earth-sized Earth mass body, Earth mass planet, surface escape velocity is 11 kilometers per second. It is enough to evaporate or melt rocky material. So when the planetesimal hits the Earth surface or planetary surface, So this kind of analysis already done in 1970s or 80s. If the impactor size is larger than 1 kilometer sized bodies, then the impactor make some deep crater, so the impact energy is deposited to the interior. The fraction is like a 10% or 20% or something like that. Other impact energy is radiated away, but some fractions deposited to the inside. But the impact energy is huge, so that it is enough to heat up planet. So here's some calculation. It's in 1980s. So this so horizontal axis is a planetary size. So in the early stage, when the planet is small enough, then the escape velocity is small. So that even if impact occurs, they don't melt. But once the planet size becomes larger than Mercury or Mars, then the impact velocity is high enough to melt outer layer. So this red line, red curves express the adiabat, so the which means that they are already melt and heat is transferred by convection. Of course, in this case, like a short-lived radioactive element like alumina-26 is not included, but even without the alumina-26, just a planetesimal impact make the very deep magma ocean. So then once the some fraction of the interior is melt, then the core mantle separation occurs, and also through the impact, CO2 atmosphere is created by the impact. So this graph shows that just a planetesimal accretion, but the giant impact case is also similar. But in the case of pebble accretion, situation is very different. As I said, pebbles suffers a strong gas drag, even in the protoplanetary disk. But around the planet, there may be a thick atmosphere, so high density atmosphere. So the impact energy is dissipated. So the impact velocity becomes small. So they don't make the impact generated magma ocean. Instead, this process heat up atmosphere. Yeah, actually, we did many orbital calculation and setting the primordial atmosphere. Primordial atmosphere means that if the planet embedded in the protoplanetary disk, solar nebula, then some hydrogen helium atmosphere is created. Of course, after the disk has gone, such kind of light hydrogen atmosphere may escape and disappear. But if planet are embedded in the disk, some hydrogen helium atmosphere is created. Then the pebble accretion velocity is slowed down. And this is our preliminary result. When the planet mass is like a lunar size on the Mercury, then the impact velocity is still escape velocity. So it increases as the planet grows. But when the planet size becomes like a Mercury or Mars, then such a primordial atmosphere is created. Then the gas flux becomes important. So that eventually impact velocity is determined by terminal velocity, not the escape velocity, terminal velocity. And the density of the atmosphere becomes denser and denser, so the impact velocity becomes smaller and smaller. It's typically, so the in the case of Mars, impact velocity like 3 kilometers per second, but after that, impact velocity is like 1 kilometer per second or less. So that we cannot melt the surface of the planet. But as I said, the impact energy is deposited to the atmosphere. So atmosphere is heat up. And also, through this process, pebbles are ablated and disrupted, so which means that the heavy element, a solid particle, are distributed to the atmosphere. So the atmosphere becomes very optically thick. So the greenhouse effect may be important, and if the greenhouse effect is really effective, then due to the such warming, greenhouse warming, magma ocean may create it or not. But how to make the magma ocean is totally different from the case of the planetesimal accretion. Okay. So another issue is isotope variety. It is one of the weak point of the pebble accretion. As I said, in the case of pebble accretion, pebbles are formed in the outer region, and they migrate inward, and the planet shares the building materials. So the building materials should be the same, almost same. So that we cannot make the difference in the isotope ratio, like oxygen isotope or D/H or something like that. Only the difference is that the pebble formation is inside out. As I said, in the inner region, pebbles are formed very quickly and migrate. And so in the outer region, pebble growth is very slow. So in the early stage, a pebble come relatively near place. But in the later phase, pebbles come from the very distant place. So there's some time difference. So if we can make the like a barrier in some time, then we can make the spatial difference from the such time difference. So this is I took from the paper by Steve Desch, and he suggested that when the Jupiter is formed sometime, then after that, solar system is divided to two parts. Of course, when the Jupiter is formed, pebble cannot pass through. So in a region, just also the pebbles are separated. If that kind of things happens, then we can make the isotope difference. But I don't know if we can make isotope variation consistent with observation. So it's always a big issue. Okay, so I don't know the answer, so I want to ask you good idea or something like that. Okay, so finally, I talk about the water delivery. As already you know that the Earth is very much depleted in volatiles. So here's some estimation by the Rhine River. For example, so water H2O. So ocean mass is just 0.02 weight %. It's very small. So maybe some water can exist in the transition zone in the mantle, but maybe at most like 1 weight % or something like that. So it's really dry. A planet in outer region, like icy satellite and also Uranus, Neptune, they should have the like a half and half rocky and ice component. But the Earth is very dry. Also, so this plot is a. This plot It's so composition normalized by alumina is highly refractory, and then we compare the composition of Earth is compared with solar composition. For the refractory element, solar composition and Earth composition is almost same. But for carbon and nitrogen, they are in general volatile, so that they are highly depleted. In the case of carbon, like 1,000 times, or nitrogen, maybe 100,000 times depleted from the solar composition. So in a sense, this is very natural. If we consider the solar nebula propagated disk, then the ice condenses only beyond a few AU. Because the pressure is very low, so the condensation temperature is really low. And also the NH3 and CO2, CO, they condense in very cold region. So that it is natural that the Earth doesn't have such volatile element. Because if we consider pebble accretion, if they pass through the snow line, ice line of CO2, then the CO2 sublimate and disappear. And if it passes through the snow line, H2O just dissipate. But still, this kind of argument it's not so clear, because this is based on the equilibrium condensation model. But some, like there are refractory carbon, like refractory organics. If the in the like meteorite, we find a carbon, but in a very complex form. It's a complex, like a complex molecules. Also, in the interstellar cloud, there are many refractory carbon, called like carbon grains. They are very refractory. But if such kind of refractory carbon is abundant, then the Earth should be like a carbon planet. But actually, it is not a carbon planet. It is still a big argument. But as long as we consider the equilibrium condensation model, water and carbon and nitrogen condense in a very cold region, only in the cold region. So the question is, if this is correct, the question is how the water and the carbon nitrogen was delivered to the Earth. In the classical model of the planetesimal accretion, often discussed that like small bodies, like asteroid near the snow line, they may include some fraction of the water, such as carbonaceous chondrite or something, and they are scattered by Jupiter and hit the Earth, then the water is delivered. This is one idea. But if we consider pebble accretion, situation is different. So such kind of icy material should be delivered by pebble accretion. So we did some simulation. As I said, if we consider the accretion disk, so after the million years, disk temperature is low enough that the snow line can be inside of 1 AU. So that initially, icy pebbles sublimate like a few AU or 5 AU. But in a later phase, icy pebble can reach the planet. We did some 1D dust growth and migration calculation, and to calculate, estimate the water weight fraction of the planet. We find that the water fraction is about half that it is a very simple idea. When eventually snow line passes through the, for example, 1 AU, at that time still a lot of icy materials exist in the outer region because the icy pebble formation is inside-out manner. But once it passes through the 1 AU, after that, icy pebble comes. But we can calculate the total mass of the icy pebble at the time of the snow line passage. After that, pebbles migrate, then we can calculate which fraction of pebbles are created by the planet. So that we can exactly estimate how much icy material can be delivered to the planet. So the total mass of the icy bodies at the passage of the snow line, it depends on the initial disk structure. So once we set up the disk evolution model, actually we use the self-similar model. Model, it's a very standard for the prototype disk structure. Then calculate the water fraction for the Earth. So there are some disk parameter, but we set up the initial disk size and the initial disk accretion rate onto the star. So disk accretion rate is proportional to the disk mass. So the higher m dot means that the relative massive disk. A typical value of the mass accretion rate onto the star is 10 to the minus 8 solar mass per year. But the observations show that there are some distribution from the 10 to the minus 9 or 10 to the minus 7. So the region where the red or yellow, it expresses that the icy fraction is 10 to the minus 4 or 10 to the minus 2. So the value is consistent with our Earth. So we find that if the disk size, initial disk is small, relatively small, like 10 or 20 or 30 AU, actually it is consistent with recent simulation of the star formation or disk formation. And if the initial disk accretion rate is relatively high, then we can make the relatively dry Earth. On the other hand, if the disk size is large enough or m dot is initially low, then the Earth becomes an icy planet, not a rocky planet. And also, this calculation predicts that the ancient Mars is more water-rich because if the Mars is located outside of Earth, so the snow line passage is earlier, so the more chance to accrete the icy material. Okay, so let me summarize my talk. So pebble accretion model, new model, may solve the radial drift barrier. It's a very serious problem in the classical model. But the problem is that how to make the seed of the more than kilometer-sized bodies. And in the classical model, Jupiter formation timescale was also a problem because in the outer region, planetary formation is inside out. So the 5 AU, 10 AU, so the core accretion is very slow. And the estimation show that it's very difficult to make Jupiter's core within the disk lifetime. It was a big problem. But if we consider the pebble accretion, Jupiter's core can be formed in 100,000 years or something like that. A typical disk lifetime is 1 million years or 10 million years. So it's short enough. But then we need to overcome the pebble isolation mass issues. And the diversity of exoplanetary system also can be created very easily. But then we need to discuss the detailed disk evolution model because pebble accretion is affected by the gas drag or scale height or something. It depends on the detailed parameters of the disk. On the other hand, classical planetesimal accretion model, gas structure is not so important. And if the pebble accretion scenario is correct, then it may change the picture of the early Earth formation and its surface environment. Okay, thank you very much.
So now we have time for questions. Do you mean just to talk in the mic so that it's recorded?
Well, it's a mixture of questions and comments. So I guess the first thing that I want to ask you is you talked about pebble accretion in the framework of large, what I would call large pebbles, but these objects don't exist in the meteorite record. So that has given rise to a kind of a model where the pebble accretion in the inner solar system anyway is fueled by much smaller particles, so that would be chondrule-sized particles. So how does it impact the timescales that you're talking about for growth of embryos and potentially Earth-like planets with smaller particles?
Yeah, that point is already discussed by Alessandro Morbidelli or other people, and the argument is that as already discussed, when the icy pebble passes through the snow line, then the icy envelope evaporate, and only small silicated particles are distributed. And the silicated particles are not sticky, and we can make just a millimeter size at most or something. So the small silicated particles are ejected, and if they accumulate, then they can explain the chondrule size or something. We don't discuss about the. I don't discuss about the heating mechanism. I mean, just a size.
No, but I'm talking about just pebble accretion with chondrules, millimeter-sized particles.
Actually, it's not so slow because as I said, icy pebbles carry a lot of silicate component. So the silicate component, its migration is slow, but the density, number density is high, because they are carried by the very rapid icy particle. So the growth time scale becomes a bit longer, but not significantly.
So the second comment or question is, you said that pebble accretion cannot be reconciled with the isotope variation in the inner solar system. So I don't think that's right. So there's a paper by my group which came out only a few months ago or a month ago in Nature where we actually show a relationship between the size of the planets in the inner solar system or asteroids and embryos and their isotope composition. And what we are saying is essentially this observation is a prediction of pebble accretion if the size of the different bodies is a function of their accretion timescales. In this scenario, for example, we make a number of say 100 kilometer size bodies by gravitational or streaming instability in the very early stage, and that has the composition of the inner disk. As time moves forward, we basically have particles drifting from the outer solar system to the inner solar system, and then we're fueling the growth of these planetesimals. And as bigger bodies are being created, they're exciting the smaller bodies, which are then being lifted from the midplane, and then we're quenching the pebble accretion or the chondrule accretion. So we create basically this time sequence of isotopic composition related to the accretion timescales. So I think it's fully consistent with pebble accretion.
Oh, I see.
So that's the second comment.
Oh yeah, so thank you very much. I haven't read the paper and
Okay, so the third question is in the last scenario that you talk about the migration of the snow line. To me, it seems that it requires that the Earth did accrete within the time scale of the disk. I mean, is that correct for me to?
Actually. Even if we consider mass-sized bodies, for example, if we assume that the planetary embryo grow until up to mass size in a disk, and after that they collide with each other, even if we consider the mass-sized bodies, this fraction is almost same. So so such bodies collide with each other. Then Mother's body should have the similar amount of water. If the escape of water through the giant impact is not so significant.
No, but I guess my question was more that does this happen, this migration of the snow line, during the disk lifetime?
Yeah.
Okay, so then you need the sizable planets to be there when there was still gas.
Yeah.
Okay. Yeah. So, and just the last thing I wanted to ask you with respect to this diagram here, how would the early formation of Jupiter affect the drift or the flow of icy pebbles, and how does that impact your model?
Yeah. Once the Jupiter is formed in outer region, of course the pebble flux stop. So after the Jupiter formation, of course the icy bodies cannot reach the in the region. So we also did a simulation with formation of Jupiter. We set up artificially this timing or that timing. Then we find that if the Jupiter formed very early, then everything very dry. But if the Jupiter formed late, already this kind of only saturation occurs. Because once the icy bodies accretion start, then the pebble accretion is very fast. So it's really quickly saturated. So the formation of Jupiter makes some 0 or 1, something like that.
Other questions? Don't be afraid, even if you're not a specialist of pebble accretion.
Yes, how does this fit with how do you explain the formation of the moon with this global model?
Yeah, it's a good question, yes. If we make Earth only by pebble, then how to make a moon is a big issue. Right, that's right. Actually, we are doing another calculation. If the Earth's body is formed by only pebbles, then how fast is the spin rotation? And we find that it's really fast. It's comparable to the Earth-Moon system. So it is close to the rotational instability. So it's a very extreme idea, but if the Earth is formed by pebbles, Stokes number like 0.1 something, then so the pebble accretion is very asymmetric. So in the case of planetism, once it hit here, of course another planetism should hit here. But the pebble accretion is really asymmetric. So the resultant rotation is very fast. So that if it happens, moon can be formed by fission or something. Yeah, it is an extreme idea. But another idea is that the pebble accretion stop before Earth size, like a pebble isolation mass, something like that. Then after that, when the disk has gone, then they part of each other and start giant impact. It's a usual consideration.
Just a quick one. When the pebbles enter the atmosphere, are they so small that they sort of burn up and then they're never really accreted to the planet because you need this large body to start with? Is that a problem?
Oh yeah, it's also a problem. If the Earth's atmosphere is completely isolated from the disk gas, then eventually they accrete. But of course, the in the primordial atmosphere from the nebula, in that case, atmosphere is continuously connected to the disk nebula. If some recycling occurs, then the solid material just gone. It's recycled and disappear. But already Chris Omel and other people did a simulation. So relatively in the inner region, such recycling is very important. So the planet cannot accrete anymore. But in the outer region, such recycling is weak. So the 1 AU is it's a very delicate region.
At a certain point, you mentioned that with a hot atmosphere, what could actually partially melt the mantle and generate a magma ocean. So I was wondering if this has been quantified and what would be the depth of this magma ocean formed by this mechanism.
It's not so clear, but many years ago, like 70s, 80s, Chushiro, Hayashi, or other group, they discussed about the magma ocean created by the thick hydrogen, helium atmosphere. It's many years ago. And they found that the surface temperature of the Earth can be like 3,000 Kelvin or something like that. Then the magma ocean was really deep. There are only several papers. So in principle, it is possible, but it's not so clear to me. So it depends on timing of the disk depletion and other things. But in principle, if the Earth-sized body is embedded in the solar nebula, then the just primary atmosphere, hydrogen helium atmosphere, can melt Earth very easily.
Are there any other questions? No. I have a question.
Oh, yeah.
Yeah. It is about the delivery of water to the terrestrial planets. So I completely understand the argument that if the snow line moves inward, then you can bring icy planetesimal to the disk. But I have a question. There was a paper by Kudzi and Sisla like 10 years ago, in 2010, something like that, that said that when you start to grow icy pebble, icy material, the icy material can penetrate in the inner solar system very rapidly, and in quite a short time, less than 1 million years, you can remove a lot of the icy material from the outer solar system, simply because pebbles drift very rapidly. So you take the ice from the outer solar system and you put it inside the slow line, so that after 1 million years, you get an outer solar system that becomes like ice poor because water ice has come inward. So my question is that, is it possible, do you think that with the pebble scenario, this mechanism happened before the Jupiter formation, so that a lot of the water from the outer solar system can go in the inner solar system?
Yeah. So the that effect is already included in the disk size. So large disk means that even after 1 million years, there's still a lot of reservoir in the outer region.
Okay.
Yeah, but if we start from the small size, then as you said, pebbles already depleted. So because pebble formation timescale is shorter in the inner region. So if we consider this small disk, so pebbles are quickly formed and they just migrate and disappear. So if we start from the small sized disk, so when the snow line pass, already most of the icy material already depleted. So the Earth cannot accrete a lot of ice.
Oh, okay.
Yeah, that kind of effect is included. Yeah, we calculate dust growth and migration consistently.
So in this model, we do not need a Jupiter to make a water-poor Earth, like proposed by Morbidelli et al.
Yeah, if we start from the very small disk.
Okay. Thank you. Any other questions? Okay. Thank you very much again.
Yeah.